Hi, folks. So, this chapter, following the one we just covered about how to name compounds, gets into how we start to measure them, how we're going to classify them with atoms and moles and percents. So, we're going to start off with the basics of how do we weigh them and quantify them. We're going to start right now. So, as I said, it's very important to know what do we have and how much of it do we have. So to start things off, talk about weighing atoms. So that if we were to microscopically shrink ourselves down to the atomic level so that we can easily quantify atoms and weigh out individual atoms, we got a scale that could measure small enough that we're going to weigh out an individual molecule by itself without any of its twins, any of its other little bits. We'd be weighing out its atomic mass. And with that in mind, since the weight of 1 gram would essentially be millions of billions times bigger than a single molecule, we find it easier to use what's called an atomic mass unit, an AMU. The basic conversion factor, and there always has to be a conversion factor. We always have to have something to convert to and compare off of in all of our many different math things. Just like we reference a meter to the speed of light, so it's referenced to a constant we can compare. We have to have some way to compare an AMU to a gram. So 1 gram is equal to 1 AMU is equal to 1 gram over 6.02 times 10 to the 23rd. Essentially, 1 AMU is 1.661 times 10 to the negative 24th grams. We specifically calibrated 1 AMU so that 1 atom of carbon 12 weighs exactly 12 AMUs. And because of the conversion factor between moles and atoms that we'll see, 1 mole of carbon 12 would weigh exactly 12 grams, assuming we had only carbon 12. Now, carbon 12 weighs a little bit less than the 6 protons, 6 neutrons, and 6 electrons that it has because of the intermolecular forces consuming some of the mass. So that's why a proton and neutron actually weigh a little bit more than 1 AMU. But we can't just say 12 grams on the periodic table because there are isotopes of carbon. And if we tried to grab 1 mole worth of carbon atoms, we wouldn't get all carbon 12. We would get occasionally some carbon 13, even some carbon 14 thrown in there. And so we give their average weight as carbon being 12.011 AMU. Well, because of the nature of AMU, grams, and moles, we can figure out the weight of 1 mole of carbon. Because of what we've qualified a mole as. An AMU per atom has a 1-to-1 relationship as gram to mole. So if I have 12 AMUs in an atom, that's also 12 grams per mole. So there's an easy way to convert atoms to moles. And so when we look at, instead of the atomic mass, we can look at what we call the molar mass. the mass on the mole scale. That if the average weight of one atom of carbon is 12,011 AMU, 1 mole of carbon would be 12,011 grams. So essentially, when we look at our periodic table, we look at the bottom, the mass, the atomic weight is at the bottom is also its molar mass. Those two things are interchangeable. Now, if we wanted to get the mass of a larger molecule, all we have to do is we take the weight of each individual element and sum up each of the molar masses, taking into account their various subscripts. So, carbon monoxide has 1 carbon atom and 1 oxygen atom. So we take the weight of 1 carbon and 1 oxygen, we add them up, you get 28,010. Now, mind you, most times we can round to the nearest whole number, or at least to the tenths decimal place, and still be pretty safe. But in these examples, I've gone ahead and given the whole numbers. I'm looking at methane, which would be 1 carbon and 4 hydrogens. We have 12,011 again, but hydrogen being 1008, we'd have 4 of those. So adding 4 of those gets a total mass of 16,043. So that's 1 molecule would be 16,043 AMU, but also a mole worth of methane would weigh 16,043 grams. So, when we calculate our molar mass, keep as many significant digits as allowed by the least accurate mass. Now, almost every problem in just about all of chemistry will start by needing to calculate some molar mass. Anytime you get a mass, you almost always need to convert into molar mass, into moles. So we need to become intimately aware of how to calculate molar mass. Now, we can do the same thing with a molecular mass as we could with an ionic compound. Just because this is actually a 3D pattern grid of always going outward crystal doesn't make it any harder to calculate. We are just going to calculate each individual atom, taking into account their ratio between each other, as according to the subscripts. We don't need to account for the charges. We don't need to know that sodium is +1 and chlorine is -1. Even if that did matter, the electrons are so small, we usually ignore them anyways. But in a neutral compound, they counter each other out. So 1 electron here, -1 electron there, gives you a net 0. Now, but since these are not a discrete molecular formula, but the repeating unit, we're actually calculating the formula mass. So the mass of that small repeating unit. But so sodium chloride, we put sodium at 22.990. We get chloride at 35.45. Now, because the 35.45 is only known to 2 sig figs, 4 sig figs, 2 after the decimal, we can only keep those 2 after the decimal when we add them all together. Magnesium chloride, well, there's 1 magnesium and 2 chlorides. Once again, 2 sig figs after the decimal means we have to round to 2 sig figs after the decimal. Once again, you might be able to round it to the nearest tenths place and still be good, but I would not suggest you rounding these guys to whole numbers, as we're going to, especially with the 58.44, we're losing a lot of the nuance there. That could really start to throw your numbers off. But okay, so quick reminder. Moles are a convenient way of measuring our atoms. Using our moles, we can calculate the mass of any compound. And then we can convert a mass of atoms or atoms to a mass. But the key thing is it always goes through moles. Everything will go through moles. We cannot bypass moles. If I wanted to figure out the total weight of all people in the stadium, you can't just count the number of people because each people weigh a little bit different. You might be able to count people based on age and classifications, but you would have to find a way to start grouping people together. These people weigh about this average mass. These people weigh about this. We have this many children, this many women of this age, this many men of this age. You can kind of class them together. The same way, we cannot just conveniently convert grams to grams because each atom weighs a little bit different. And so we have different amounts of each guy. So we almost always have to go through moles. So for moles, if you multiply moles by molar mass, you get grams. But if you multiply moles by Avogadro's number, we get atoms. Rewriting them as two equations, you see little n is our moles times the number of Avogadro gives you atoms per molecule. Or atoms / molecules. And if you do the n times molar mass, you get the mass. I put it as little m. Now, here's an example of doing just that. We can use Avogadro's number to convert from molar mass to moles to atoms and back and forth. So if I have 3 moles of carbon dioxide, how much would it weigh and how many molecules would it contain? Hopefully, the equation is the molar mass of CO2 is the molar mass of carbon plus 2 times the molar mass of oxygen. Well, the molar mass of carbon is about 12. The molar mass of oxygen is about 16, so 2 times 16 is 32. 32 plus 12 is 44. If you notice how I set that up, the 3 moles over 1 times 44 grams per mole. The reason I do that is because moles on top, moles on bottom, you cancel out. Then you're left with just grams. 3 times 44 is 132. Otherwise, we put in 1 mole, how many molecules are there? Well, there's 6022 times 10 to the 23rd molecules per 1 mole. Once again, with moles on top, moles on bottom, I multiply 3 by 6, I get 18. I turn 18 back into scientific, and that's 1.8 times 10 to the 1st. Combine 10 to the 1st and 10 to the 23rd, you get 10 to the 24th. So real quick practice. If I have 36 grams of water, how many molecules of water must there be? Let's look at that real quick. So, 36 grams of H2O. So, molar mass of H is about 1. Molar mass of O is about 16. So the molar mass of H2O is 1 times 2 plus 16 grams per 1 mole. So I started with 36 grams. So let's start by writing 36 grams over 1. That's grams of water. Now I want grams on bottom. So I got 18 grams of water. 1 mole of water. Those should have canceled out. We can keep working. We don't have to do this separate this into 2 steps. We can keep working. 1 mole of water, that's Avogadro's number of water, is 6,022 times 10 to the 23rd molecules of water. That's moles. So 36 divided by 18 is, you don't know, 2. 2 times 6 is 12. So my answer should be 1.2, technically 044, but 0.2 times 10 to the 24th molecules. And as you see here, whoa, it's worked out conveniently. Now, here's someone's practice. Finding the molar mass. Fe2O3, KMnO4, and 0.25 moles to molecules. KMnO4. Okay, let's look at these. To do this, we need a periodic table. We cannot do this on our own, and neither do I expect you to ever do this on your own. Let's grab one. Let's see. Mind me. Nope, that's not good enough. Okay, well, no, that's good enough. Older book, but it will still be just as valid. So, iron. I'm going to write down 55.85. Iron, 55.85. And then oxygen, 55. Well, actually, oxygen is going to be 16.00. I'm just rounding these guys to the nearest decimal places. K, or to the second decimal. Okay, way over here. 39.098, which rounds to 39.10. 0 and Mn. Mn right here, 54.9380. So we're going to 94. 54.94. That right there is all we need. Those are the only ones we need. If I want to know what is the molar mass of iron 3 oxide, we're going to take 55.85 times 2 plus 16.00 times 3. And we're going to sum those up. Now, do I expect you to be able to do that in your head? No. That's why we have calculators. Some people could, but I'm not asking that of anyone here. So we do that, we get 159.7. Actually, well, yeah, 7. Let's say 70. 70, and that is grams per mole. Let's do this. Let's do the same thing with our potassium. For a molecule, one molecule means we're going to mean AMU, but it's still the same process. We have 39.10. There's one of those. 54.94. There's one of those. And 16.00. There are 4 oxygens. So let's do that. 39.1 and 54 and 94. And 16 times 4, we get 158.04. And that is AMU in one molecule, or one formula. One little cluster of these guys weighs 158. Now, the last thing, turning a quarter of a mole of this into molecules. We do not actually need this molar mass. To turn moles into molecules, all we need is Avogadro's number, because Avogadro's number is the same regardless of what moles we have. So we're just multiplying this number by Avogadro's number. We don't need the molar mass at all. And so we get 1.5, let's say, yeah, that's where we'll have to round. 1.5 times 10 to the 23rd molecules, or formula units. And that is that. So, with that in mind. The last thing I'm going to talk about in this video is the last thing we can really do to individual molecules. And that is to calculate percent composition. Now, a percent is not a hard thing. A percent composition is just a specialized version of a percent. If I say, what percentage of students pass my class? You would calculate it by calculating first, how many students pass over how many total students did I test? Well, if I'm talking about percent composition of elements, I'm going to take the total mass of that given element divided by the total mass of that compound. So how much does that guy contribute versus how much does everything else contribute? So if I say my hat makes up 10% of my body mass, you would have to weigh my total body mass and then weigh my hat, and you'll be able to see the veracity of that statement. And of course, there's always the factor of 100 to get it into a percent. So if I'm looking at iron 2 oxide versus iron 3 oxide, iron 2 oxide is made up of 77.8% iron by mass, while iron 3 is 70% iron by mass. Even though there is more iron, 2 molecules for 1 molecule in iron 3, there's 3 times as much oxygen. So 1 unit, essentially the oxygen, it's iron to oxygen, 1 to 1.5 atoms, while in iron 2 it's 1 to 1. We can clearly see the amount of oxygen is going up. And so that's why the mass percent of iron is going down. So how we calculate that? The mass of iron divided by the mass of iron plus the mass of oxygen. In iron 3, the mass of 2 irons divided by the mass of 2 irons plus the mass of 3 oxygens. Now, calculating a percent by mass of an element helps us determine what that compound is. Each unique compound has a set percent composition of each element. If I did not have 4 oxygens per 1 manganese per 1 potassium in the last compound, it would not be potassium permanganate. It would be something else. So everything, if I'm looking at the ratio of carbon to oxygen, it could easily tell us the difference between carbon monoxide and carbon dioxide. they're always going to have a set ratio of carbon to oxygen. We can also use the percent composition to calculate amount of a given element present if we know the percent composition. If I know this is the byproduct, and the byproduct will have a set percent composition, we can figure out how much of that guy should we be collecting. This can be very useful when we determine a formula from an unknown compound. Now remember that the mass percent of each element should all add up to 100%. So because iron was 77.8, oxygen must have been 22.2. You add those up, they round to 100. So one last practice problem, just to finish this off. Write them down. 300 grams of Hg2I2. So mercury, 1 iodide. That's 183.8 grams of mercury. What's the percent? And then 50 grams of zinc chloride, 48% zinc. And then we're going to want to know the mass of the zinc. Okay. So let's look at that. We're going to finish with that. Okay. Now there's two ways to go about this. Because we know the formula, you could absolutely look up the molar mass of mercury and the molar mass of iodine. And if we do that, 2 mercuries, 2 iodines, we could figure out the weight percent of mercury. However, given we have a total and we have a individual, we can just go 183.8 divided by 300 grams, and we multiply by 100. What is my mass percent? 183.8 divided by 300 times 100 puts it at 61.3%. A little over half. Even though iodine weighs a lot, mercury weighs a little bit more. The other one is if I have 48% and I want to know what is the mass of zinc, I can set this over 50 times 100. Well, how do I solve this? I can go put that over there, put that down there. So we have 48% divided by 100% times 50 grams equals the grams of zinc. So 48 divided by 100 times my 50 puts us at what mass of zinc should it be? 24. It should be 24 grams of zinc collected. 24 grams of zinc. And that should make sense. A little bit under half. A little bit under half of 50 is 24. Half of 50 is 25, so it's a little bit under 24. That is where we will stop. When we finish up, we will start by looking up empirical formula.